Welcome to the E-Padhshala lecture series in computer science. We are looking at the computer architecture course. So, this module is an introduction to multiprocessors. So, the learning objectives of this module are to discuss the need for parallel processors, to discuss the different types of parallel processors and the main issues to be considered. So, looking at the overview of the uniprocessor topics that we have covered so far, we have looked at different methods of exploiting instruction level parallelism, starting from the fundamental method of pipelining and looking at different ways of overcoming the hazards associated with pipelining. We have also looked at other issues like how we can use dynamic branch prediction, how we can look at out of order execution, how we can look at multiple issue processors and different other techniques like speculation, which will help us exploit the instruction level parallelism that is available in programs. After looking at different techniques for exploiting instruction level parallelism, we also looked at how thread level parallelism can be exploited. So, we looked at different types of thread level parallelism like fine grained multi-threading and coarse grained multi-threading. Fine grained multi-threading is wherein you switch every clock cycle, you switch from one thread of execution to another. Whereas, coarse grained multi-threading is you keep continuing to execute one thread of execution. Whenever you have a stall coming in, then switch context, you switch to a different thread of execution. But both in the case of fine grained multi-threading as well as coarse grained multi-threading, if you are only going to issue instructions from the same thread to the processor, with so many resources available with the processor, we may not actually be making use of all the resources available. So, then we looked at another technique which is called SMT or simultaneous multi-threading, where we try to combine the concepts of both ILP as well as TLP, and we try to issue multiple instructions from multiple threads of execution in the same clock cycle. So, that is how we try to exploit both the instruction level parallelism as well as the thread level parallelism available in programs. If you look at the performance implications of SMT, single thread performance, even if you are looking at SMT, a single thread performance is basically probably to go down, because if you are looking at one thread of execution happening, because of caches, branch predictors, registers, because all of them are being shared between the various threads, this effect can be mitigated by trying to prioritize one thread. But while fetching instructions, thread priority can dramatically influence the total throughput. A widely accepted heuristic which is called the I count, which will basically fetch such that each thread has an equal share of processor resources has been used, but you will still find that the single thread performance will go down, probably go down. So, we look at even with 8 threads in a processor with many resources, we will find that SMT yields only throughput improvements of roughly 2 to 4. And example architectures are Alpha 21464, the IBM Power 5 and Intel Pentium 4, which have used SMT. So, design challenges associated with these types of processors depends on how many threads we are going to use. So, we have to use enough number of threads, many to find enough parallelism, but however mixing many threads will compromise execution of the individual thread, which we have already pointed out. And you also have a problem with the front end, which is the instruction fetch. Though we try to fetch as far as possible in a single thread, that is in order to maximize the thread performance, this will actually limit the number of instructions available for scheduling from other threads. So, and the other problem is we will have to look at larger register files, because we are looking at multiple contexts of execution, and we always try to minimize the clock cycle time by increasing the frequency, and because you have many threads of execution available, you will have a lot of cache conflicts coming in. So, how do we handle all these cache conflicts? All these are design challenges associated with our SMT processors, which try to exploit instruction level parallelism as well as thread level parallelism. So, in essence, SMT is not a true parallel processor, though it enables better threading. For example, it may enable better threading up to about 30%, and the OS as well as the applications perceive each simultaneous thread as a separate virtual processor, physically there is only one processor and there is only one copy of each resource, and you try to virtually produce an illusion that there are multiple resources available for every threads. So, in order to overcome this problem associated with the SMT, because we know that in spite of doing all this, we do not really get too much of improvement in performance, can we look at the other paradigm which we have already mentioned. Remember that when we looked at thread level execution and when we looked at different ways of exploiting it, we had two paradigms possible. One was simultaneous multi-threading, other one was chip multiprocessors or multi-core architectures. So, can you look at multi-core architectures providing a solution here? Because you know the other problem that we have is it is not possible to keep increasing the clock frequencies beyond a certain point. As you keep increasing the clock frequencies beyond a certain point, which means you are going in for more and more deeply pipelined circuits, your heat problems crop up, the clock problems crop up, and you are going to have a lot of stalls that are going to come in. The stalls are going to be more significant in terms of the number of clock cycles that you will have to wait. Because of all this, we will have to look at paradigm shift from SMT to multi-cores, for the simple fact that even if you go in for doubling of issue rates above the current issue rates of 3 to 6 instructions per clock cycle, which means you are going to about 6 to 12 instructions clock cycle, which is extremely difficult, wherein you have to issue 3 or 4 data memory accesses per cycle. You have to rename and access more than 20 registers per cycle, and you will have to fetch 12 to 24 instructions per cycle. With doing all this, you may not still be able to achieve too much of improvement in performance. And the very fact that many of the applications these days are multi-threaded, and the general trend in computer architecture these days is to shift towards more parallelism. So, all this gives you an advantage of going in for chip multiprocessors or multi-core architectures. So, people have shifted from SMTs to multi-cores, and simultaneous multi-threading can be adopted in the individual cores also. So, if you compare a multi-core processor and a simultaneous multi-threaded processor, if you look at multi-core, since there are several cores here, each may be smaller than and not as powerful as the original superscalar processors supporting simultaneous multi-threading, which we have discussed earlier, but they may be easier to design and manufacture, because even you can even take the off the shelf processors, a thoroughly tested design, and you can make multiple copies of it. You can put multiple cores on the same chip. So, that becomes a multi-core. So, you do not have to really look at designing it from scratch, and it is also great with thread level parallelism, because even if one core supports a single thread of execution, when you have 4 cores, you have 4 threads of execution happening, with each thread having individual resources. And if a core can support 2 threads of execution, then with 4 cores you can even have 8 threads of execution. On the other hand, if you look at a simultaneous multi-threaded processor, it is an extremely complex superscalar processor. It may give you great performance on a single thread, and it still tries to only mostly exploit the instruction level parallelism, and we have already discussed enough disadvantages associated with instruction level parallelism, and though it is very useful, there is a limit to how much you can exploit your instruction level parallelism. So, basically the computer architects have shifted to CMPs with support for SMT also. So, we are looking at multi-cores. Multi-cores are nothing but parallel computers on a chip. It is not that parallel processors are new to the industry. Parallel processors have existed for many decades. Only thing is, in those days when you look at parallel processors, they were independent machines which had to communicate from one machine to another machine. So, the communication delay was too high and all that. So, these days when you are looking at multi-cores, it is just parallel computers on the same chip, and because you have multiple cores on the same chip, the interconnect delay, the communication delay is drastically reduced when you look at multi-cores. So, when you look at the traditional definition of a or a parallel computer, the traditional definition of a parallel computer goes like this. A parallel computer is a collection of processing elements that cooperate and communicate to solve large problems fast. And it is not that it is only we are looking at large problems these days. Now, even our desktop processors, our laptops or mobiles, all of them look at only having multi-core processors. It is not that powerful workstations alone look at multi-core processors. Any processor, whether in the embedded domain or looking at a laptop or your personal mobile devices, all of them look at only multi-core architectures these days. So, generally when you look at parallel computers, the questions that are to be answered by a parallel in a parallel computer, the design issues that you will have to decide are: how large a collection are you going to use, how many parallel computers are you going to use, how many computers are you going to connect together, how powerful are the processing elements, how do they cooperate and communicate with each other, how are the data transmitted among the various cores or various processors, what type of interconnection are you looking at, and what are the hardware and software primitives for the programmer, and what is the programming model that you are going to adopt, and how does it this programming model translate into performance. So, these are the general questions that we normally discuss about parallel computers. So, if you look at the popular Flynn categories, there are different ways in which you can categorize a computer system. One of the most popular categorization is based on Flynn's categorization. So, this depends upon the number of instruction streams you have and number of data streams you have. So, the first classification is a single instruction stream, single data stream, SASD, which we basically refer to as a uniprocessor. So, there is only one single instruction stream, one control unit and one data memory, and this is a traditional uniprocessor. And in a traditional uniprocessor itself, you can try to overlap the execution of different instructions and increase your throughput by going in for pipelining. So, the second category of computers is your MISD, multiple instruction stream, single data stream. So, you are looking at multiple instruction streams. So, you can have several functional units or several processors which will work on a single data stream. So, basically you do not have any commercial processors that are available which follow this architecture. You can say that the streaming, if you look at a specialized streaming processor, this may somewhat satisfy this type of architecture. The third category is your SIMD, single instruction stream, multiple data stream. So, you have only one single instruction which is operated on multiple data streams. So, examples are your ELIAC 4 CM2. This follows a very simple programming model. It has very low overhead, it has a lot of flexibility. You can just look at integrating a number of custom circuits, and this is basically the process that has been used in all your multimedia instructions and vector processors that we know. So, all the multimedia instructions that were introduced by Intel basically try to exploit the SIMD model of execution. Then you have your last category, which is MIMD, where multiple instruction stream, multiple data stream. So, you have multiple instruction streams executing on their own data streams. So, both of them are can have multiple instruction streams as well as multiple data streams. So, you can have many examples for this: Sun Enterprise 5000, Cray, T3D, your SGI Origin, all of them are examples of MIMD. So, these architectures are very flexible because you are looking at multiple independent processors, each having their own instruction stream and having their own data stream. So, it is very flexible. So, you can connect any of these processors together, and you can simply look at off the shelf microprocessors. You can pick up off the shelf microprocessors, connect them by means of an interconnect, and you have an MIMD style of architecture. So, MIMD is the current winner and it is the most common parallel computing platform that we look at, and multi-core processors that we have today basically fall under this category, though they may try to exploit a lot of instruction level parallelism, though they may try to exploit an SIMD style of processing by giving support for data level parallelism. So, if you look at the different types of MIMD style of architectures, you basically have two types of MMD style of architectures: centralized shared memory architectures and distributed shared memory architectures. So, if you look at centralized shared memory architectures, it basically follows a UMA architecture, that is uniform memory access time. So, first of all, they are shared memory architectures. So, if you look at multiple processors, the memory that is available is shared among the multiple processors, that is one thing, and it is a centralized shared memory architecture. So, the memory is available in a centralized location and that memory is shared by all the processors. So, irrespective of which processor tries to access the memory, you know it is going to take the same time to access the memory. So, that is why they fall under the category of UMA, which is uniform memory access time. Basically, they are also called symmetric processors, symmetric shared memory multiprocessors, or SMPs. This is the first category of processors. In this type of processors, the interconnection is traditionally through a bus. You have a very simple interconnect like a bus connecting up all the processors together. It is a very simple interconnect, but the problem is a scalability problem, because if you have too many processors connected on the bus becomes a bottleneck, because all of them will have to communicate through a common bus. So, that becomes a scalability issue. That can be solved by having a hierarchical bus. You have different ways of solving it. And it definitely provides a simpler software model if you look at centralized shared memory architecture. The other one is a decentralized or distributed memory architectures. So, in this case what happens is the memory is still shared. So, they are say decentralized or distributed shared memory architectures. So, the memory is still shared, but you distribute the memory among the various processors. So, what happens is one memory will be local to a particular processor, but it will be remote with respect to some other processor. So, if you are looking at the memory access times here, you cannot have a uniform memory access time, it has to be a non-uniform memory access time. So, these processors are called NUMA processors. But basically because of this decentralization of your memory, you get more memory bandwidth and there is lower memory latency. If you try to access your internal memory, there is lower memory latency. And the drawback of this is of course the longer communication delay if you have to access a remote locations memory. And another drawback is that the software model is more complex than your UMA style of architectures. So, if you look at the two types of architectures, so the first one that we mentioned is a centralized shared memory architecture or a symmetric shared memory architecture, an SMP, symmetric shared memory multiprocessor, where the memory is centralized, the IO space is also centralized, and you can see that all the processors have access to this main memory as well as the IO system, and the interconnect is normally through a bus. And as you can see, all the processors will take obviously the same time to access any location from memory. So, this is a UMA style of architecture. So, the second style of architecture that we discuss is the distributed or decentralized architecture, where as you can see the memory is distributed among the various nodes or processors. So, if you look at a memory that is local to a particular processor and if it is trying to access a location there, then the access time is going to be different. But if it has to access a location from a different memory, it has to go through the interconnect and then access the memory. So, the delays are going to be non-uniform. So, that is why we talk about a non-uniform memory access. So, if you look at the models for communication, so having looked at two different types of architectures, the centralized shared memory architectures and the decentralized shared memory architecture, now we look at the various models that are used for communication. So, when you look at your shared memory with non-uniform memory access, the NUMA address, both these are of the shared memory architecture. So, basically what happens is whenever you are looking at a shared memory model, there is logically one address space, whether they are available in one place or they are distributed among the various processors. They may be physically distributed, but it is logically one address space, and the communication basically happens through the shared address space. So, one processor if it wants to communicate some information to a different processor, it just writes into the shared address space and the other processor reads it. So, the communication basically happens through shared address space. And the other model of communication that you can have is a message passing multicomputer, where you can have separate address space per processor. So, in this case what will happen is, one processor, if it wants to communicate with the other processor, it will send a message to the other processor through the interconnect. And you look at the programming model which uses a message passing interface, it can invoke software with what are called the remote procedure calls or RPCs. So, these are the two major models that we look at for shared memory architectures. It can either be through a shared memory. So, write it into the shared memory and other processor reading it from the shared memory, that is one model. The other one is a message passing interface. So, both these you often have libraries. For if you look at message passing interface, you have libraries like MPI, which is the message passing interface. And if you look at shared memory communication, you have your OpenMP, which is a standard library to use. And your message passing interface is also synchronous communication, since communication causes synchronization between two processes, because this a message is being transmitted by one process, the other one reads the message. So, there is an explicit synchronization happening between the two processes. So, if you look at the performance metrics for communication mechanisms, the major issues that we will have to look at with respect to performance, you have three different parameters. One is the communication bandwidth. So, your communication bandwidth should definitely be high. Whatever communication mechanism you use, your communication bandwidth has to be high. And this communication bandwidth is limited by the processor, the memory as well as the interconnection bandwidth obviously. And the other factor that you will have to look at is communication latency. How long does it take to transfer data from one node to another node? This obviously affects the performance, because the processor will have to wait. If the data does not reach the other point, other processor, this processor will have to wait till it receives the data. So, it affects the performance of the processor, and it also affects the ease of programming, because you will have to give more thought to overlap communication and computation, so that you are able to avoid the latency associated with your communication. So, that the processor does not get stalled, you may have to give more thought in overlapping the communication and the computation, so that the communication latency is hidden to you. And there is a lot of overhead associated with communication with respect to many machines. So, the third one is, if you are not able to avoid the communication, there is definitely a latency that is going to happen because of your communication. Can you think of some methods of hiding this latency? Say for example, even when we looked at a memory hierarchy, you cannot avoid your main memory or a secondary storage, because they are going to satisfy your capacity requirements. So, we looked at different techniques as to how to avoid the communication latency or hide the communication latency associated with your slower memories. So, likewise here, the moment you talk about a multiprocessor system, the moment you talk about the necessity for communicating from one processor to another processor, you cannot avoid the communication latency, but you can always try to look at techniques which will try to hide the communication latency. So, how can a mechanism help hide latency? So, this will obviously increase the programmer's problem, because you will have to look at techniques which will try to hide the communication latency. So, examples are, you can overlap the message send with computation, you can prefetch data so that you are able to hide communication latency, and you can also switch to other tasks if you have a stall coming in. If you have to wait for some data, then do not simply waste time, you can switch to other tasks. So, these are some of the methods which we have already seen with respect to our memory hierarchy, which can be used to hide your communication latency. So, if you look at the advantages of the shared memory communication model, the shared memory communication model is basically compatible with our symmetric shared memory hardware. You have an ease of programming when communication patterns are complex, or even if they vary dynamically during execution, and there is an ability to develop applications using familiar SMP model attention, and you will have to pay attention only on performance critical accesses. So, all these are advantages of shared memory communication models. It also has lower communication overhead, better use of bandwidth for small items due to the implicit communication and memory mapping to implement protection in hardware rather than through the I/O system, and hardware controlled caching to reduce remote communication by caching of all the data, both shared and private. So, all these are advantages of your shared memory communication model. Now, what are the advantages of your message passing communication model? In the case of message passing communication model, the hardware can be simpler, especially compared to your NUMA style of architecture, and the communication is explicit here, because you are sending a message from one processor to another processor, point to point communication happens. The communication is explicit here, so it is simpler to understand. Whereas, in the case of shared memory, you are just writing it onto shared memory and somebody else is reading it. So, it can be hard to know when communication is happening and when it is not happening, and how costly that communication is. All that is a difficulty with respect to your shared memory interface. And also, because of the explicit communication, you can focus attention on costly aspects of parallel computation, sometimes leading to improved structure in your multiprocessor programs. And synchronization is also naturally associated with sending messages, reducing the possibility of errors introduced by incorrect synchronization, and is also easier to use sender initiated communication, which may have some advantages with respect to performance. So, all these are advantages of your message passing interface compared to your shared memory interface. So, both of them have their own advantages as well as disadvantages. Now, if you look at the third type of parallel programming model, that is the data parallel model. This is basically used in the case of your SMD style of architectures, where you are looking at a single instruction stream and multiple data stream. So, in this case, operations can be performed in parallel on each element of a large regular data structure such as an array. So, you have one control processor which broadcasts to many processing elements. So, they each one of them have their own data memory. So, they have different datas, and there is one control processor which broadcasts the same instruction to all PEs. And you can also look at a little flexibility by means of conditional flags, so that you can decide whether that processing element is going to actually perform that operation or it need not perform that operation. And data is obviously distributed in each of these memories. And you have a number of data parallel programming languages which you can use to this style of architecture. And this has led to this model of SIMD programming has basically led to what is called the SPMD model of programming, which is called the single program multiple data. So, if you, for example, if you are looking at a loop and you have multiple iterations of the loop, you can execute the same program, but you can execute multiple iterations of the loop. So, all processes execute identical program, but they will operate on different sets of data. So, if you look at the different programming models that we have looked at, a shared programming model, a message passing program model, and a data parallel programming model. To summarize what is meant by a programming model, a programming model is basically conceptualization of the machine that the programmer uses in coding and applications. So, it basically indicates how the various processes cooperate and communicate and coordinate their activities. It also specifies the communication and the synchronization operations that happen between the various processes. And if you look at multi-programming, there is no communication or synchronization at the program level happening when you are looking at multi-programming. Whereas, when you look at the other types of models, say for example, shared address space or message passing, shared address space is like a bulletin board, because anybody can write into the shared address space and anybody can come and read that from the shared address space. So, it is like a bulletin board. Whereas, if you look at a message passing interface, it is a point to point communication. So, it is like letters or phone calls which are explicit point to point communications. And the third programming model that we looked at, which is the data parallel programming model, is more regimented. It is more compartmentalized, it is more regimented. You can perform global actions on data, and it is normally implemented with either shared address space or message passing. So, now having looked at the different styles of parallel architectures and having looked at the pros and cons of each of these architectures and having looked at the various programming models that are available, we will try to identify the problems associated with parallel processing, or what are the main challenges associated with parallel processing. We have already identified that your communication bandwidth should be very high, your communication latency should be as low as possible, and if at all you have a communication latency, then you should try to come up with techniques which will try to hide the latency associated with your communications. Challenges of parallel processing. So, the two major hurdles of parallel processing are you obviously have limited parallelism available in programs. So, all your programs are not going to be completely parallel, and you also have a high cost of communication. So, the second problem, if you have these two problems, how do you illustrate the effect of these two problems? Your problem of not having enough parallelization and your problem of communication latency. So, in order to illustrate this, let us look at the Amdahl's law, which tells you that your speed up overall is going to be 1 by 1 minus fraction enhanced plus fraction enhanced by speed up enhanced, where fraction enhanced is the original percentage of the program, that is the original component, which is going to be speeded up. Suppose if you have a problem like this, you have, say for example, your 80% of the, you need a overall speed up of 80%, and you want to find out how much of percentage of the code has to be sequential or parallel if you want to use 100 processors. So, I am using 100 multiprocessors, I want to get an overall speed up of 80, I want to find out how much of my code can be sequential. If you try to do the calculation, you find that the fraction enhanced or the parallel component of your program should be 99.75%, which means that only 0.25% of your program should be sequential. So, with only 0.25% of your program being sequential and with 100 multiprocessors, we assume that either you use only one processor or use all the 100 processors, you find that you are still able to get only 80% overall improvement. So, that tells you the importance of parallelization. So, we would always try to look at how much ever parallelism that can be brought into your coding. So, the second problem is the communication latency. So, if you consider a 32 processor multiprocessing system operating at 1 gigahertz and only 0.2% of the instructions involve a remote communication reference, which takes 400 nanoseconds per access. In spite of this, you find that even with the most optimistic calculations, you will find that the remote references, if they are not there, the multiprocessor will be 2.6 times faster. So, that shows you the effect of your communication latency. So, how do we handle this? We will see if we can use caches to handle this problem, which will try to give you advantages of having increased bandwidth and reducing the latency of access, but you have other problems associated with caches, which we will elaborate in the next module. So, to summarize, we pointed out the limitations of instruction level parallelism and thread level parallelism, and we have looked at the need for parallel architectures. We have looked at the major categories of parallel architectures. We have looked at the different programming models associated with these parallel architectures. We have also pointed out the main challenges associated with parallel architectures. Thank you.